Um, all right. Hello, everyone. Hi. My name is Megan Jaluka. I'm a graduate student at the University of Washington Astrobiology program. And today we're, of course, having the Astrobiology Careers Panel event. So thank you all so much for coming. And for those of you that are on Zoom, today we have 5 panelists who all graduated from the University of Washington with degrees or certificates in astrobiology. So from left to right, well, except for you. Yeah. So from left to right, this is Dr. Victoria Meadows. She did not graduate from the University of Washington with a degree in astrobiology because she is the program director. And then we have Dr. Elena Amador, Dr. Eddie Schwederman, Dr. Tyler Robinson, and Dr. Max Showalter. And so to start this event, before we get to the question session, I'm going to allow Dr. Meadows to give you some background on what the astrobiology program here is at UW. And then we're going to have each panelist talk for about 5 minutes about their career and their interest in astrobiology or their current interests today. And so with that, I will hand it off to Dr. Victoria Meadows to tell us about the University of Washington's astrobiology program.
All right. Well, hello, everybody. And yeah, thanks for joining us. So at this University of Washington Astrobiology Careers Panel. So I'm going to talk, maybe I'll just manually, how do I do this? It's not advancing. Yay, that works. Okay. So the first question, of course, everybody asks is, what is astrobiology? It sounds really new and exotic. And it is, in fact, the study of life in the universe, its origin, its evolution, its distribution, and its future. And I often get ribbed as the director of an astrobiology program. People say, well, isn't this a field in search of a topic? Because we don't have any aliens yet. So, how do you actually do any work on, the study of life elsewhere in the universe? But really what astrobiology is it puts the scientific underpinning under that search. So it helps us to decide where to look and what to look for as we search for life beyond the Earth, either elsewhere in the solar system or on extrasolar planets around other stars. So that first question of where should we look for life brings us to this idea of habitability, habitable environments, habitable planets, places where life could, in fact, exist. And so, for example, that could be looking for life in the subsurface of Mars. For example, we think there might be liquid water present, or on extrasolar planets, trying to understand all of the different factors that allow a planet to maintain liquid water on its surface over time. And those can involve interactions with the planet, its star, and its planetary system. And then how can we tell if a planet is inhabited? Well, if you're thinking about sort of the typical alien here, these aliens are great because they actually have technology and they're able to say hello to the universe. They're able to say hi to us, to transmit signals. So they're actively, in theory, trying to make communication with us. However, technology evolves over a very long period of time, and so there may only be a small amount of alien life out there that can actually talk to us. So instead, what we think is probably going to be more typical is the type of life that we see in our biosphere all around us and in the Earth's history, which is just organisms that are just going about their daily business of metabolizing. They haven't developed radio telescopes. They're just simply modifying the environment as they live. And if you listen to them, you would only get a deafening silence, right? So we have to figure out some other way of trying to detect these things on other worlds or in our solar system and beyond. And so really we're looking for what we call signs of life, and that's really life's environmental impact, how life has taken an environment and modified it in some potentially detectable way, whether that's modifying something in the rock record on Mars or potentially looking at the spectrum of an extrasolar planet. So in this particular case, these little lumpy things are actually colonies of organisms. They're called stromatolites. They have cyanobacteria. They're responsible for making them. And that cyanobacteria over billions of years is responsible for the oxygen that you're breathing today. So that oxygen there's a lot of oxygen. And so that has modified the environment in a very detectable way. And so astrobiology now underpins a lot of NASA planetary science. We started back in about 1998 when people thought, well, this is kind of strange, but, okay, fine, we'll go with it. But nowadays we are definitely mainstream. And so NASA planetary science missions and astronomy missions are all now focused on this idea of the search for life elsewhere, either the search for habitable environments, life in our solar system, or studying extrasolar planets. So the subtext under this is there's actually quite a lot of money in this area now as well. And so this is really a growth area of science. And it's exciting too. So the UW Astrobiology program We also have a very long history, and you are in a 25th anniversary celebration event here. So we started back in academic year 1998, and we developed this astrobiology graduate education program for both training the next generation of astrobiologists, but also doing undergraduate education and scientific research. This is a massively interdisciplinary program. We have 11 departments spanning 4 different colleges. The College of Arts and Sciences, College of Engineering, College of the Environment, and the School of Medicine are all involved in this training program. We offer a graduate certificate, which can be done both by PhD students and master's students. And we offer a dual title PhD in the home department in astrobiology, which is not only coursework, but also research rotations at labs across the world, and also these workshop experiences where we go out into the field and learn about different fields. So the UW, of course, in doing all of this, also has to host a world-class Center for Astrobiology Research as well, which we do. So we have a lot of active research projects and a lot of faculty involved in that. If you want to learn more about us, you can go to our website there, and it's easily found by just typing Washington Astrobiology into Google, and you'll pretty much get there. Okay, so I will just finish up here and say that our program graduates have awesome careers and are in fact awesome themselves. And you've got 4 examples behind us here. But just sort of a quick example of, Jeff Bowman is now an associate professor at the Scripps Institute. He's famous for our kick-ass shot of him kneeling on the ice in the Arctic, harvesting things called frost flowers, where we may have microbial life. Rika Anderson is an associate professor at Carleton College. Ava Stuken has gone to Scotland. And then we have a suite of other people here, but I'll just go over our actual presenters here today. So Elena Amador, she is a systems engineer and a deputy science chief for Mars Curiosity rover. Max Showalter is the deputy policy director looking at sort of sustainable use of natural resources in Washington State. Ty Robinson is an associate professor at the University of Arizona, looking at how to observe the Earth as an exoplanet, essentially understanding how we might see Earth-like planets, but also with fingers in habitability and biosignatures as well. And Eddie Schwieterman, who is an assistant professor at UC Riverside, very much into biosignatures on extrasolar planets and finding new and novel ways to look for life. So that is our panel today and who you're going to hear from. So I'm now going to transition into my bit of the panel. So I'm now giving a separate talk. I'm not just running over. So I'm going to talk a little bit now about sort of my career and what interests me now, what I'm actually working on, and then each of our panelists are going to do the same after me. Is it the same presentation or are they going to swap? Yeah, it's a presentation. Okay, great. So anyway, here's our panel. And so I'll talk a little bit about me. So these are little sort of vignettes of my life and the places I have been, just as sort of visual reminders for me. So I started out on Sydney's northern beaches in a place called Bulgola Plateau above Bulgola Beach, and this is an aerial shot of Bulgola Beach. It's lovely. But as a little girl growing up in Australia, I was one of those hyper nerds with the glasses who would sit at the top of the driveway with her dad's binoculars, looking at the moon and just being blown away. So I was very interested in that. I went and did degrees in physics at the University of New South Wales and Sydney University. And then at the end of my PhD, I was incredibly lucky to get a postdoctoral position at NASA's Jet Propulsion Laboratory with someone called David Crisp. And David worked on both Earth science and Venus science. And he sort of introduced me into planetary science, which was really fantastic because that's really where I wanted to go. I couldn't do it in Australia. Actually, I ended up commissioning an instrument on a telescope. So I come from instrumentation and observing, but he, allowed me to be one of the first people to actually see the surface of Venus in near infrared light. So I did that at the JPL. I also worked on the Wide Field of Planetary Camera 2 instrument, which corrected Hubble's defective optics back in the day. It was an instrument that was put up to correct that. And after working at the JPL for a while, I then transferred over to the Infrared Processing and Analysis Center at Caltech, which was just next door, basically, where I worked on the Spitzer Space Telescope. So that was an infrared space telescope, and I was what was called the uplink scientist there. And so I was responsible for being the liaison between the scientific community and the engineering team on the spacecraft to make sure that we had the right commands on the spacecraft, that we could command the spacecraft in a way that made sense for the scientists. So that was my role. And by the way, I didn't need any special training from that. I just came straight in from being a scientist. And then ultimately I came to the University of Washington in 2007 as a professor here because they advertised for a professor in astrobiology. And I had been running at that point for about 7 years as the lead of a big research center in astrobiology. And it's this thing called the Virtual Planetary Laboratory, and that's what I'm working on right now. So I've been running the Virtual Planetary Laboratory now since 2000. And in the next 5 years, we're going to be focusing on what the next flagship mission, the Habitable Worlds Observatory, will be able to do. So you've probably heard of the flagship missions in astrophysics, the things like the Hubble Space Telescope or the Spitzer Space Telescope or Chandra or whatever. This is the next one that is being planned. It's called the Habitable Worlds Observatory. It's going to be a big telescope in space that is able to actually image terrestrial planets, so planets a bit like our Earth, around other stars. And so that's incredibly exciting because it means we can now start to study other worlds with these telescopes. So my team is going to be trying to identify new biosignatures, and actually Eddie is a task lead for that, to interpret them in the context of the environment, to try and figure out if the planet's fooling us into thinking we have life when we don't. We're going to get to simulate the local solar neighborhood of planetary systems and actually, try and tell if, a planet has real life on it or a false positive life. Can I tell the difference? And then we're going to have this assess task, which will help us do this in a statistical way to say, look, I'm really much more confident there's life on this planet than on other planets. And Ty is a co-lead for that task as well. So that's what we're going to be focusing on in the next 5 years, is really just setting the stage for building this telescope and making sure that it can do the astrobiology science that we want to get out of it. So I will pass over now to okay, the next speaker. Okay, I guess it's Elena.
Take the microphone. Yeah, and I can start talking a little bit about things that aren't on my slide. So I'm Elena Amador French, and I graduated in 2017 with the dual title PhD in Earth and Space Sciences and Astrobiology. And something I left off of the slide, but hearing Vicky say it, I would like to repeat it, which is that I also started as the nerdy little girl who was very interested in the natural world around us. And I asked my parents lots of questions like, where does the water come from and from the faucet? Is there a river under the house, or why are the mountains there? Why do rocks look like this in riverbeds? So just very curious about the natural world around us. And that's why I ended up in the field of geology, essentially. So my bachelor's degree is in Earth and Planetary Science from UC Santa Cruz. In case there's undergrads in the room, I hope there are, or I hope they're listening. I also had research experience as an undergraduate at Ames and at SETI, where I got to use spacecraft data to look at the planet Mars. And that really set me up then to come here to UW for my PhD. And I've tried to summarize what I did for my PhD in a few questions. So really, I was trying to ask, can we use surface signatures to understand the past environmental conditions of a planet? And can those signatures be used to infer habitability? So I was very interested in Mars and using the near infrared to understand the mineralogy of Mars and understand if there were certain signals in the mineralogy or signals that the mineralogy gave that would imply something for habitability. So I took that. I got to do a lot of incredible field work. I traveled to Iceland, to Hawaii, to Italy, studying what the surface signature were for different habitats, essentially. And then compare that to spacecraft data of Mars. It's okay. And so after that, after doing a lot of amazing field work, I went to Caltech for a 2-year postdoc, and I got to apply that knowledge very specifically. So this knowledge of what surface signatures can tell us about habitability, applying that to selecting the landing site for the Mars 2020 rover Perseverance. And this rover is tasked with going to a once habitable environment and collecting samples that have the best chance of potentially having life. If Mars ever had life, this would be the place to go, and these are the samples to collect. So Perseverance is there now doing that. But I got to spend my postdoc mapping the surface of Mars in these specific landing site areas with the Mars 2020 science team. And as you can imagine, it was very contentious and exciting. And I got to be part of debates in meetings where we all fought about why our landing site was more exciting than somebody else's. My landing site was not selected, but it was a very interesting experience nonetheless. But during that time with the Mars 2020 science team, I got to do my independent research, but then I got to be part of this group, this science team that all had the same, objective to study Mars, working together to push the knowledge of astrobiology. And I loved that. I loved working with the missions. I loved working with the teams. And so when I finished my postdoc, I got hired on at JPL to join the Curiosity rover team, part of their science team at JPL, as a science operations coordinator. And as Vicky was saying with Spitzer, I think you were saying, basically I was the scientist in the room. I am the scientist in the room at JPL, helping translate between this international team of scientists. We have 200 scientists across the globe who call in every day to do rover operations with Curiosity. They're not there at JPL. At JPL are the engineers who write the sequences and uplink those sequences to the rover every day, and also are maintaining, the health and safety of the rover. But they're all engineers. They don't speak science necessarily. So I get to be the one in the room translating between the two and making sure that our science measurements are making it all the way up to the rover to be executed, and vice versa. I talk back to the scientists about why we might be constrained and can't quite take the measurement that they really want to take because it might break the arm, or we might we might get stuck in the sand, for example. So it's a really fun role where I get to go between these two different disciplines every day. And it's tactical operations. We uplink every day. And so it's fast, quick paced. You have to know what your objectives are and be able to communicate them quickly, assess anomalies. It's really fun. And so the question that we're constantly asking ourselves is, how do you optimally do science on another planet? You only have so much resources, so much time. And so it's a fun puzzle. And I'm currently the deputy science operations team chief for that rover. But being at JPL as a systems engineer, I do my operations work and my Curiosity work, but I still get to do a little bit of research when I have time, because there's many things going on at JPL. I get to participate in other proposals for future missions. I get to help analyze data from other rovers as well. So I get to do a little bit of everything. And that's my spiel. Let's see. Pass it over to Eddie.
Yep. And as the slides are changing, I can also start just with some personal anecdotes about how I got interested in astrobiology. And when I was a kid, one of the most impactful things my dad ever did was take me out fossil hunting, me and my sister. And we searched for fossils in the Devonian Shale in Pennsylvania, and we lived in New Jersey at the time, and also in Missouri, where my dad's side of the family lived. And so the first thing I wanted to be when I grew up was to be a paleontologist. And somewhat naively as a child, I thought this was bad because all the dinosaur bones would be dug up by the time I would get a PhD. And so I thought, well, I'm going to study astronomy because there's no way we'll figure out everything before I can make my own contribution. And that sort of crystallized, that interest in astronomy crystallized for me in high school in about 2004. There was a transit of Venus, and the very last part of it intersected with the East Coast. I was living in Florida at the time, and I took my telescope with its solar filter to the beach. And as the sun was rising, the transit of Venus was finishing. And by the way, none of us here will ever see another one. There was another one in 2012, but they're so far apart. Anyway, when this was happening, I thought, wow, this is a planet going across the face of the star. I'm seeing this. Who else is looking at this? Is someone looking at our planet going across the face of our star from some interstellar location? And so I knew, of course, that to get into astronomy, you have to study physics. So I went to kind of a smaller private school, the Florida Institute of Technology, for my undergrad, studied physics and astrophysics, and did some research experience for undergraduate programs. One that was at Florida Tech on cataclysmic variable stars, and then one at Lowell Observatory as part of the NAU, Northern Arizona University REU, on comets and looking at comet rotation periods and rotation rates. And I got very interested in planetary sciences. Mostly, I was just so interested in the idea of interdisciplinary science. And so it was just perfect for me to apply for the University of Washington. And it was so great that the University of Washington had an astrobiology program. And I've benefited immensely from it. So what this slide is showing is my academic track, which is sort of a traditional academic track. And so I studied with Vicky on modeling Earth as an exoplanet, on photochemical climate modeling of terrestrial exoplanets, amongst other things. Very happy with how that turned out, because as part of one of our external speakers for the astrobiology program, Dr. Tim Lyons from UC Riverside came and gave a presentation about his new Alternative Earths grant. And I ended up applying for a fellowship to work with him at UC Riverside and got that. I also, through that experience, met one of the co-Is of that grant, Chris Reinhardt at Georgia Tech, and also spent a year postdocing with him. And then amazingly and magically converted my postdoc at UCR to a faculty position, which I can talk about a little bit more. But my wife and I were in part had a two-body problem, and we both, again, magically, independently converted our first postdocs at separate institutions independently into faculty jobs. And so at Riverside, I'm in the Earth and Planetary Sciences department. I find this also really good in terms of the spirit of UW's astrobiology program, because while we don't have an official dual track PhD like we do here, at Riverside, we have in the Earth and Planetary Sciences department, we have a breadth of topics that does touch on the origin, evolution, distribution, and future of life in the universe. We have people who are geochemists who are studying, the evolution of Earth's atmosphere, the coevolution of life in the environment. We have paleoclimate folks who look at how the evolution of the marine biosphere has impacted the climate, and in addition to a couple exoplanet folks. And my particular research spans, kind of a interdisciplinary range of topics. So one is modeling Earth as an exoplanet. Another is considering signs of life, possible signs of life on an exoplanet, and all of the sort of processes, planetary processes, astrophysical processes that could lead you to mistakenly attribute the presence, a signature on that planet to the presence of life. And how would we disambiguate that signal and identify that process? And even if you don't care about life at all, you should be concerned if there are multiple processes that give you the same signal, because we want to study terrestrial exoplanets in general, not just the habitable ones. So by thinking about life, by viewing planets through the lens of life, we can actually learn a lot of things about the planets that don't have life. I think about that in general with photochemical models, because so many of our observations are going to be dependent on the models that we use to interpret those observations. And those models have uncertainties in their fundamental inputs. And so reaction rates, et cetera. And so with some of my colleagues, we partner with folks who actually do those laboratory measurements or the ab initio computational measurements and think, how could we improve, and what are the lever points to most improve those models? And then I think more generally about habitability. I'll go through this. I have a team of very talented students, 4 PhD students who work on a breadth of topics, including modeling habitable and non-habitable terrestrial planets, the TRAPPIST-1 system, for example, of thinking about novel biosignature candidates that could accumulate in the atmospheres of planets and be detectable, either possibly, with the very few targets we'll have with James Webb Space Telescope, but also for future observatories, for ELTs, for the Habitable Worlds Observatory. And I co-lead a sub-working group on biosignature possibilities as part of that effort. Students who are working on these fundamental inputs and the sensitivity of our model interpretations to those inputs, and a postdoc, Shami Sai, who's incredibly talented in looking specifically at sub-Neptunes and the wealth of data that we're getting from these most common planets in the universe that we have no analog to in the solar system. And I'll just end with this graphic about alternative Earths. So I mentioned Tim Lyons. I met through an astrobiology seminar at the University of Washington. And so I think Liza mentioned this when we were having lunch. Definitely go to those and go to the lunches and talk to people. And it's overlaps with what VPL does, but its center of gravity is very specific and complementary on looking at the evolution of Earth, the co-evolution of life and the environment on Earth as an analog to the vast array of possible biogeochemical states we could find inhabited exoplanets residing in. So that's where I'll end.
So good afternoon, everyone. It's a real pleasure to be here, and it's an honor to be here for the 25th anniversary of the UWB program, and thanks to the organizers for having me out. My name is Ty Robinson. I'm a professor at the University of Arizona in the Lunar and Planetary Laboratory in the Department of Planetary Science. Fun fact, my tenure packet is actually due today, and so I'll be starting on that after this presentation, apparently. I didn't know this about Eddie, but I likewise also started off thinking that I was going to be a paleontologist. Spent a lot of my younger years going to like short summer camps, digging up dinosaur bones that the instructors had conveniently inserted into like sand. But something that I learned about myself around about high school is that I don't really like being outside that much, and I really don't like having dirty hands. I wash my hands a lot. And I think it was my mother who then asked me to reflect on whether or not I wanted to be some kind of field paleontologist, and I realized no. That kind of does a disservice to paleontology because there are many ways of being a paleontologist, some of which involve being in a lab in a very clean environment, but I didn't know that at the time. This is my map of where I have been over the course of my career. It's come full circle, literally, and I didn't intend it to do that. So a lot about my career are kind of examples in very happy accidents, and sometimes intentionality. Lots of wonderful, great advisors and mentors that I've had over the course of my career that I'll try to briefly highlight here. I grew up mostly in the state of Arizona, north of Phoenix. At the time, Arizona had a nice program that incentivized students to stay in state for their undergrad careers, and so I opted to go to the University of Arizona in Tucson, which is the lower dot down there where my journey sets out. Also, because this is an astrobiology related presentation, notice the color coding here is done to the geological eras of our country. So I started off studying engineering there, and I kind of quickly learned that I was more interested in how things work than making things work. So I jumped over to studying physics and mathematics as an undergraduate. As is often the case with undergraduate programs, you have to / get to take general education courses, and I was taking a general education course in the humanities. And the instructor for that course, to this day, I don't know why, but really felt like I was engaged. At the time, I felt like I was just like doing a thing that was required of me, but maybe I was engaged in the class. And so she pulled me aside and asked me about my motives for taking the class, what my interests were. And I said, I'm a physics student and I don't know what I'm going to do next. And she said, well, maybe you should get involved in research. And so this is one of the happy accidents that happened over the course of my career. I have no idea where I would be today if it weren't for that professor pulling me aside and having that conversation. She happened to have a good friend that was in the astronomy department at University of Arizona that she introduced me to, and then he brought me into his lab. And so I did, for hourly pay, I did instrument development at the University of Arizona for a few years there. I learned as part of that process that working on instrumentation wasn't the most interesting thing to me personally, given kind of my broad interest in physics. I really liked when I was in my physics classes doing derivations. And so I got introduced to a faculty member at the University of Arizona who did modeling and computer simulation, and that was much more aligned with things that I was interested in. So I worked on a research project there that ended up in kind of a capstone project. And then I really had no idea what I wanted to do next. And I saw all of these examples of people studying their, getting their undergrad degrees, and then they go on to grad school. And I really knew absolutely nothing about what grad school was or where I should apply. I did a little bit of asking around in the department, and I got some suggestions. And I so kind of scattered my applications to the wind with very little intentionality there. I thought, maybe I want to work on planets and how planets form, but I was like, maybe I want to work on black holes. And so I was fortunate to get into a few programs that I visited. Rory Barnes, who's sitting in the back of the room here, was at University of Arizona at the time and helped me with my decision to come to the University of Washington. And so you can see that I made my journey up to the University of Washington. So here with the astrobiology program, it was a great fit for my interest in planets. In my first year and some change in the astronomy department here, I tried out some different research projects, but none of them were quite the right fit. And then another happy accident that happened in my career was Vicki was hired into the department. And on Vicki's very first day as faculty in the department, I knocked on her door and said, "Hi, I'm Ty, and I'm going to be your graduate student." And luckily, And so luckily, Vicky had funding for a project related to studying our Earth from afar. And so I got to scratch my modeling itch, but also got to be on a spacecraft team and look at data from a spacecraft. So that was a wonderful first project. And so I benefited from a lot of great advising and mentoring from Vicky over the course of my PhD. And then it came time to do what was next. I was very much enjoying the academic path of what I was doing, so I decided to do what's called a postdoctoral position, or look for a postdoctoral position. I applied for various positions with lots of help from advisors and mentors, sculpting my applications, and secured a 2-year position at NASA Ames Research Center, where I kind of broadened my research horizons and worked on new things. After spending a couple years at NASA Ames, postdocs are usually only a couple years long. I went on to my next postdoctoral appointment at UC Santa Cruz. So you can see all my little jumps over here, if I can get my cursor, in the Bay Area. I also noticed that when I put this map together that I'm very much a child of the West. And so I've been over in the West for my entire career. After working at the University of California, Santa Cruz, I applied for faculty jobs. As Eddie was highlighting, and this is maybe something that we can revisit during the Q&A, I have a scientist spouse, and so we've always been working to balance our two-body situation so that we can both have careers that we enjoy and find fulfilling. And the place that was going to be the best bet for that was Northern Arizona University in beautiful Flagstaff, Arizona. And so I spent a handful of years there on the faculty. Northern Arizona University has a history of being an undergraduate and teaching focused university. So there were a lot of opportunities there for undergraduate research, engaging with undergraduates in collaborative research, and in honing my teaching skills. But it wasn't the best fit for some of my research interests, and so both my spouse and I decided that maybe we weren't going to stay at NAU, and then had the opportunity to move to University of Arizona 2 years ago. So I'm all the way back now as faculty where I was 2 decades earlier as an undergraduate. And I love Tucson, and it's great to be back there. So a little bit about my own work, just briefly. There we go. So I love planetary atmospheres. And so on the left are some numerical simulations that I did of starlight interacting with a planet's atmosphere. And so that's a gas giant planet that's moving onto the disk of its host star from our perspective. Again, this is done entirely in simulation. You can see the ring of light around the left side of the planet from your perspective, and that is light that's been bent by the planetary atmosphere and is coming to you, the observer. And so I spent some time studying what's called refraction in exoplanet transits, which is what this is. In the middle has to do with spectroscopy. And so at the top, you can see it's actually a plot. I'm showing you a figure here with some data where the y-axis is how bright something is and the x-axis is color. And so that's a spectrum of something that might be Earth-like. And so the points there are the data points, and they've got error bars on them. And so we're not sure how Earth-like that thing is. And so what that movie is doing is it's actually showing you a statistical approach, trying to explore ways of fitting those observations to explain whether or not, in this case, that atmosphere has water vapor in it, just like our atmosphere has water vapor in it. And then some things that I'm also working on right now that are on the right-hand side of this figure. I am a participating scientist on the chronograph instrument for the Nancy Grace Roman Space Telescope. And so that instrument is going to be looking at primarily gas giant worlds around nearby stars, trying to separate out the light from a very faint planet from a very bright star, and maybe study the atmospheres of those gas giant planets. And then kind of standing on the shoulders of Nancy Grace Roman will come the Habitable Worlds Observatory. And so I'm a member of a development team for Habitable Worlds Observatory that's going to push that technology to the next level to be able to spot pale blue dots. So to be able to spot Earths around nearby suns, to take their spectra, to look at their colors, and to understand if there are signatures of life coming from those worlds. Just to seed some ideas for the Q&A, I already talked about that I have experience with what we call two-body problems, as do many people on this panel. But I'm a professor at a university, and there have been some big surprises about what it means to be a professor at a university that I never anticipated as an undergraduate or a graduate student. For example, how much time I spend thinking about budgets, and how many reports I have to write to close out awards or to renew awards. And so there's a lot of paperwork that I never envisioned that would come with this career. But I also get to do science that I dream up, and I get to work with great students and collaborators. And so there's a very rewarding side of my career there too. So that's all I've got.
I don't have any slides, so you just have to look at me. But hi, everybody. I'm Max Showalter. I'm the Deputy Policy Director at Washington State Department of Natural Resources, or DNR. Right now, I'm thinking, what's the deal with fossils? Because my dad also took me fossil hunting as a kid, but it actually made me not want to be a paleontologist, which is maybe how I ended up where I am today. So unlike the other panelists, I'm not an astronomer and I don't work in astrobiology currently. So what I'm hoping to talk a little bit about is how I got into the field that I'm in now and some of the connections and ways that being at UW Astrobiology prepared me for that. And jumping to the punchline, I was always interested in everything and lots of different fields in oceanography and geology, despite the fossil hunting experiences as a child, and astronomy. And that's why I really liked astrobiology. And it helped, I got to tackle this big question of what's the origin of life and is it really out there? And I get to do similar things now in my role at DNR, where I get to work with foresters and marine ecologists and social scientists. And we get to think about housing and natural resource management to tackle the big challenges of climate change and how we do sustainable natural resource management in Washington State. So backing up a step, I graduated from UW Astrobiology with my PhD in oceanography and astrobiology in 2020. I came to this program because I was really obsessed with Jody Deming in the oceanography department and really liked her work looking at extremophiles, so bacteria that can live in extreme environments in sea ice. So I did my PhD looking at bacteria in sea ice, mostly in the Arctic with Jody, looking at how they cycle carbon, how they respond to chemical gradients, and how they respond to viruses that attack the bacteria. And I had a great time doing my PhD. I got to go to a lot of really cool places, got to go to Antarctica for a couple of weeks, got to celebrate my birthday on an ice floe at the North Pole, spent time in a permafrost tunnel in Alaska. And overall, I just had a really great experience. But the entire time I was in grad school, I always felt like for me, there was something missing, which was really focusing on how it applies to people's lives. So while I was in grad school, I got really interested in science policy and thinking about how we can use the science that we're doing to make tangible changes on some of the biggest challenges that we're experiencing. And especially in the Arctic, the biggest challenge that we could see is climate change. So that really got me interested in focusing on the science policy track. I also realized that in grad school, I didn't love being the person doing the research itself. I liked going out into the field, but I didn't like processing the seawater samples for hours on end. I liked doing collaborative work, and I liked things that had lots of different paces and sense of time scale. So rather than just doing one super long 7-year project of a PhD, I liked having the opportunity to do lots of different types of projects that last days, weeks, and months. And so after I graduated from UW, I did a fellowship with NOAA, the Sea Grant Knauss Fellowship, where I worked in the NOAA Office of Ocean Exploration and Research. And then came out here to Washington, I guess stayed in Washington because it was remote, came back to Seattle and started at DNR, where we get to tackle, like I said, some of the biggest challenges that I think we interface with on a daily basis as Washingtonians. So I really love my job because we get to think about things like climate change and natural resource management. And to me, what's really exciting about working at the state scale, especially in Washington, is that most of the folks that we engage with are also really invested in solving these issues. And we have a lot of leeway to come up with really creative solutions. So at DNR, we manage about 6 million acres of public lands in Washington state. Which is about 5 times the size of Olympic National Park, just to give you a sense of scale. And this includes forested lands, agricultural lands, and also aquatic bedlands. So any land on the seafloor under like Puget Sound, most navigable rivers, most lakes, DNR manages those too. So it's a huge portfolio. And we house the Washington Geological Survey. We do things like urban forestry. We do commercial leases and think about public housing. So this is something that was totally different than what I did at UW in astrobiology. But now I get to be immersed in all of these different topics in my field. And I'm rarely the technical expert in the room, but what I really love about my job is getting to interface with all the technical experts and bring their work together into plans and implementing those plans for resource management. Just a couple of examples of some of the work that we're doing that I think is really exciting at DNR. We're one of the first groups in the country, states in the country, to look at doing carbon credits on state forests to have that as an alternative model for revenue generation as compared to timber harvests. We're also working on a totally novel plan to protect kelp and eelgrass statewide for salmon habitat. So this is one of the projects that I co-lead along with our aquatic scientists to tackle preserving 10,000 acres of kelp and eelgrass across Puget Sound and the Washington coast. And then one thing that I'm really excited about too is we're also getting into the business of landscape scale restoration and climate change mitigation focused on process-based restoration. So for us, what that looks like is really looking at the riparian zones, the rivers in Washington, and thinking how we can sort of dial back the 150 years of change that have been happening in Washington that have made us less climate resilient, that have made salmon populations decline and made communities more vulnerable to changes. So we're doing things like bringing beavers back to some of these habitats so that they can help raise the water level on the rivers. We're installing large wood installations in the rivers to create new salmon habitat. And we're doing broad scale floodplain connectivity so that we can restore some of the natural processes that otherwise would be really damaging to communities or habitats. So that's just a smattering of some of the things that we're doing at DNR and sort of an alternative from some of the other things that folks are talking about today to give you a sense of the breadth of things that you can do with your interest or degree in astrobiology. Thanks. You need this? Or you have one? Okay, I'll just stay here.
Okay, so at this time, can we thank all of our panelists for their introductions? Okay, so now I'm going to go ahead and move on to the question portion of the panel. So please feel free to ask them about their careers, how they got here, benefits of having their degree and or their research and career today. But maybe will kick off the question session with a question of my own. So in astrobiology, of course, the push is for interdisciplinary science. And so that meaning we're studying lots of different fields at once instead of only focusing on one thing. And just because you maybe don't go into a job in astrobiology, I personally have found, as I'm sure you have as well, that studying things from an interdisciplinary sort of perspective can really help in lots of different other facets of your life. And so I was curious to hear from the panel about the benefits of studying a science that's interdisciplinary as opposed to focusing on one specific topic. And you can have this mic. Who wants to start?
Yeah, it's a great question.
Oh yeah.
So my title now is systems engineer. So a systems engineer looks at all parts of a problem and how they work together, how they interact, trade spaces. And so my time here at UW in the astrobiology program, I remember, I think one of my first classes with Woody Sullivan, he told us that by the time you graduate, you will be able to sit in on a biology talk or an astronomy talk or a chemistry talk and understand at a high level what's going on. You might not understand the nitty gritty details, but at a high level, you can leave the room and understand. And vice versa, you will be able to explain your research or topic to, a breadth of people. And so really what I think I got out of this program was how to be a communicator and how to talk to different groups of people in ways that they can take away the important parts of, what I'm working on. And so that's what I do every day as a systems engineer on the Curiosity rover. I need to be able to talk to the power lead or the mission lead or somebody who understands the motor actuators on our mass camera or the scientists that are asking for different measurements. And I need to be able to communicate to them. So at the end of the day, I am a communicator. And I think that's my expertise, is talking to people and making sure everybody has the information that they need. And this program basically taught me how to do that, I feel like. Does anybody else have something you want to add?
Yeah, that's a great point, Elena. I followed the traditional academic track, so I'll answer based on that frame. And I would say, the universe itself is not disciplinary, right? There's no silo between chemistry and physics and biology and reality. And so going through this program and learning from folks who are biologists and oceanographers and atmospheric scientists and astronomers gives you an appreciation of understanding the universe as it is, which, you can't discount the value of that. But also it helps you write good proposals. It helps you ask the right questions. It helps you find the best collaborators to answer those questions. And even if you don't go into a field of study that's explicitly astrobiological, as Vicky mentioned in the intro slides, astrobiology is percolated to all areas of science and planetary science specifically. So even if you're studying like the internal nature of ice giant planets, there's an astrobiology angle to that. And if you can appreciate that, you might be able to write proposals that are more likely to win and get funding. So if you go do the academic track, it's a huge utility to interdisciplinary knowledge, being able to talk in an interdisciplinary way and build interdisciplinary teams.
So I'll just say a couple of things and agree with everything that's been said before. So two things are, interdisciplinary training for me personally has really helped me with spotting connections. And so some of my favorite research that I have been able to be engaged in has happened when I was speaking with one disciplinary science about some aspect of something in astrophysics, and then talking with another disciplinary science, and then realized that the processes that are happening over here in astrophysics are the same that are happening over here in earth science, or vice versa. And then there's an opportunity to bridge the two and to kind of unify understanding across the two. And that's been a lot of fun. The other thing that's been really great about being trained as an interdisciplinary scientist, and this is related to communications, is it really helps me at parties. I hang out a lot with scientists, as you might expect. I'm kind of a socially anxious individual, and so being able to know that I've got enough of the language and enough of the understanding that whoever I accidentally get paired up with at a party and I'm going to be chatting with has been a real blessing for me.
Yeah, I'll just add that working at the interface of science and policy, interdisciplinarity is like my everyday job. Like I mentioned earlier, I'm almost never the technical expert in the room. So being able to interface with folks across lots of different topics is really valuable. And just to add one other thing is that I think having the exposure to lots of different topics at UW and lots of different disciplines really helped me appreciate and gain a better skill set in just thinking about different ways of knowing more broadly, which is something that I work with every day. We work with the 29 federally recognized tribes in Washington on a daily basis, and being able to think about indigenous knowledge and how to incorporate that into policymaking and work across boundaries is also really valuable.
Yeah, and I think for me, I wasn't trained in this program, but I created this program. But I think in my experience as the Virtual Planetary Laboratory lead, what interdisciplinarity has done for me is it enables you to tackle really big questions that a single field cannot address. And so that's super exciting. So it leverages you up into an area of science that is very broad, very connective. You talked about communication, but you also synthesize. You synthesize the information that comes in, and you make something bigger than the sum of its parts from the information that you have. And so so that has been really exciting. So there's no way without astrobiology I could have ended up leading a 70-member team addressing the question of how do I best look for life on extrasolar planets, right? So astrobiology gives you that power to be able to just address just super big questions and not sort of, not going down into the nitty gritty of a discipline, which is valuable and is needed as well. But it kind of brings you up and out into these much broader, sort of more fundamental questions, I think, to human meaning as well. And so, so I think it's good for that too. It's panel mic.
Thank you. Does anybody have questions? Yeah, I'm just going to. Somewhere I think you have 2 microphones, so I'm just going to pass you the microphone.
Hi, thank you. So speaking of big questions, I'm curious to know how the field is addressing non-carbon-based forms of life, if there are hypotheses about that, and also if that's not an interest, how is the field defining what life is fundamentally, and how does that bias the search for it?
Yeah. So I'll answer your second question first. NASA defines life as one NASA definition of life is a self-sustaining chemical system capable of Darwinian evolution. That's the standard definition. And of course, we all know that there are gaps in any definition of life, and ways to attack that definition. And it's important to discuss and think about. I would say that how are we addressing this? And this also speaks to your question about non-carbon-based life, is that kind of complementary to astrobiology is a field called synthetic biology, and the idea is by creating life, we can understand how it originated, and we might also understand the other forms that it can take elsewhere. So there are people who work on, for example, what is the minimum genome that we can create a cell with? Now that's carbon-based life. And so you asked about, what about non-carbon-based life? And so we thought of silicon-based life is the most commonly given one. If you actually get into the chemistry, you can make many, many fewer bonds with silicon than you can with carbon. And carbon just has this ability to make many types of molecules. And the number of molecules you could do that with silicon are limited. And the other thing that I often point out is, the Earth's actually very carbon poor. It's very silicon rich. And so you might ask the question, there's silicon everywhere, in terrestrial planets. So why don't we see it? Maybe that speaks to the probability of the carbon-based versus silicon-based life. There are other technical things that you can think of, like what are different solvents, and people have investigated this, and it turns out that it's harder to dissolve things in, say, liquid methane than it is in water. And there are attributes of water beyond just the fact that commonly given that, water when it freezes gets less dense and doesn't sink. There are many chemical attributes that make water favorable for a solvent as well. But it's an open area of investigation.
Yeah, so I just want to add to that and maybe get to the question behind your question, which might be, are we stuck just looking for Earth-like life, right? Or can we move beyond, the things that we see in our environment? And so in the field of astrobiology now, there's a new subfield called agnostic biosignatures. So agnostic biosignatures don't assume Earth-based life. They don't assume known metabolism. And what they try to get at is sort of fundamental properties, kind of in the chemistry and the thermodynamics of life, that are of interest. So for example, in situ, there is in agnostic biosignatures, so in situ is when we actually go to a planet, try and measure a rock or something, looking at sort of the complexity, the number of chemical reactions that are required to make a given molecule. The more of those that happen, the less likely it is that it'll just spontaneously happen in the environment. And so we actually had a great seminar, which was taped. You might want to look at it, by Heather Graham last week. It was last week, yeah. Just looking at the sort of this complexity theory of looking at that. And so that way we don't have to assume anything. We would go into an environment and say, wow, isotetramethyl whatsopropylene, that is pretty complicated. And so we're looking at that, where we don't assume that, there's something producing oxygen or whatever. And then in extrasolar planets, and this is something that many people on the panel know, we look for disequilibria in gases. So we look at an environment and we say, oh, these two gases would like destroy each other if you lock them together in a shoebox or something. Why are they coexisting together in this environment? And the answer is that there are active fluxes of these things. They're being produced all the time. And then you go to, okay, well, so what's producing them? Is it a known planetary process? And if we rule all of those out, then, maybe the life hypothesis is the correct one. But in that case, we're not assuming, again, Earth-based life. So we're trying to address that. How do we look for life as we don't know it with those sorts of techniques, looking for patterns and difficult processes and trying to find not planet, trying to rule out things that we know to be planetary processes. So we are trying to tackle that question. You want to say something?
Hi, so I'm an undergraduate freshman, and I was just wondering, um, what sort of steps can someone like me take to prepare for a degree in astrobiology? Because I'm majoring in astronomy right now, and since I see you talking about like interdisciplinary fields, I was wondering like what sort of classes can I take, what sort of internships can I do, what sort of events can I attend, so that I can better succeed in astrobiology in the future.
I guess I'll take that one first, but I think you guys probably all have opinions too. So one thing I will say is that, and it's kind of been implicit in what we've all said, but we haven't explicitly said it. But in astrobiology, you are not like a Renaissance person who comes knowing everything, right? You come with your own discipline and your disciplinary expertise. So don't try and make a degree that is a little bit of everything. Really hone in on an expertise that you can bring to a team. So an astrobiologist really is, and I think we'd all call ourselves astrobiologists here, except maybe Max, but you have astrobiology training. But for those of us who are actively working in the area of searching for life in the universe, we really are experts in our own particular area. But our key difference is we are super excited about interacting with other fields, getting information from other fields, and doing that kind of synthesis. So I think, if you're majoring in astronomy, major in astronomy. But at the same time, you might want to look at, maybe doing planetary science classes in atmospheric sciences or, in earth and space sciences. So there's ways you could, potentially branch out into other disciplines and learn a little bit more about their expertise. But don't compromise the core of your expertise in astronomy, because that's what you will bring to astrobiology. That's what you bring to an interdisciplinary team. So astrobiology is done by interdisciplinary teams, but each member of the team has their own expertise that they bring to it. But stay curious, and look for different sort of, electives and things that you can potentially do that expand those interests into areas you'd like to look at. Yeah, so I'd say that. But you're welcome to come to all of the astrobiology colloquia. We hold them in spring and summer. So look out for those. There's flyers in the astronomy building that go up. And also there's a wealth of them all recorded on our website. If you go to our website, you can see talks from, the shining lights of astrobiology who we bring here to come visit. And they give us talks, and we tell them to pitch this for a general audience. So a lot of those are quite accessible, even if you're not an expert in the field. And we encourage them to also provide an overview at the beginning, so you can learn quite a bit of basic astrobiology from the overview that our speakers give at the beginning. So there's two suggestions.
That's great. And what I will add, at least in my experience during undergrad, is talk to your professors. Don't be scared to talk to them. They're really excited to talk to you and share with you what they're working on. When I was an undergrad at UC Santa Cruz, I just went and talked to my planetary science professor after class one day and just, was asking her questions. And I was like, how can I get an internship? And she connected me with somebody at NASA Ames. And I had no experience in doing research in planetary science. I was as fresh as you can be. And there are projects for people with no experience that your professors would love to bring you into. So talk to them. And little by little, by making those connections with them, you can start getting that experience. And that experience, those research experiences, I think, are what then got me into grad school, having that in undergrad. But I remember being stuck early on in undergrad, feeling like, oh, I can't talk to this professor. I'm not an expert. I don't know, they're going to think I'm not smart enough for this, but you are smart enough, and they are very excited to teach you new things. So go talk to them.
I would add to that excellent comment from Elena that don't be afraid to ask questions when you think the professor may be assuming that you already know. So as we advance in our careers, we kind of forget what we didn't know before. And so you're not going to embarrass yourself by asking these questions. And it's very possible when you're talking to more senior people that they assume you know something that you don't, just from inertia. And so don't be afraid to ask those questions. And the other thing I would say is look into research opportunities like REUs, like NSF REUs. NASA also has a list of internships at NASA centers that you can look, and those are often pretty extensive. And you can go in the summers, but they also have ones that are off season in the academic quarters, if that's something that you can swing.
So those were all excellent points. I'll add that at every stage in your career, you really benefit from having great mentoring and great advising, and that is true from the start. And so if you're thinking about heading off on a scientist trajectory, it's important now to try to find someone who's going to be an advocate for you, someone who's going to mentor you, someone who's going to be an advisor for you. And the best way to do that often is through your courses and connecting with the professors that you meet through your courses and going to office hours. So I second all of those opinions. The National Science Foundation research experiences for undergraduates that Eddie mentioned, there's a website for that. And so that will give you summer research experiences. Before that, I would even look to see if there are any formalized programs here at the University of Washington that you might be able to get into to start doing research here at the University of Washington. I suspect those do exist. They at least existed when I was here previously. And then to add to Eddie's comment, the NASA positions and USGS and probably many other federal agencies advertise those on Handshake amongst other places. And so you can look on that platform for kind of undergraduate research experiences.
As a biologist, I hated learning this myself, but two skills that are going to be useful for you in every field in astrobiology are basic math and basic programming. So I recommend at least doing a little bit of that before you get to the end of your undergrad career.
Okay, the question is, are there any outreach programs for middle or high school students to learn more about this program and astrobiology?
For middle school, yeah. So we think
Pre-undergraduate.
pre-undergraduate. We do have, well, I mean, not right now, I wouldn't say, but we can certainly develop some. We are doing the open house, yes. Yes. So we are going to have an open house in the summer. And students in those areas of education are absolutely welcome to come. So we're going to have an open house for astrobiology. We're going to open up our labs. We're going to talk about the research that we do. We're going to have presentations from people. There'll be a planetarium show. So that is coming up. I don't know roughly which month that's going to be in at the moment. August. Okay, that's going to be in August. So you're welcome to come to that. And that way you can learn more about the program and come talk to the astrobiologists and see the research we do and, get your hands dirty in the labs and all that kind of sort of stuff. So, so I would recommend that for just now. But I don't
speak to the specific science if that person happens to.
Yeah. Okay. Specific science in it.
Okay. Hi, I'm Megan. So if you are in Seattle, you should look at the Pacific Science Center. They have lots of different programs there for you to both learn and participate in learning. And I think Ty can also speak more to working with the Pacific Science Center, as a matter of fact. I guess the other thing that I would say is that since now I'm on this panel, I started doing research when I was in high school, and to do that, I just actually talked to my high school teachers who helped me to start my own research project. I was in astronomy, so I did something called the National Young Astronomers Award program, which is like a amateur astronomy award. So I would look, if you are in astronomy, look to your amateur astronomy programs, look to clubs. And also NASA runs a ton of different opportunities in astrobiology for people that are in the pre-undergraduate portion of their careers. And maybe, I don't know, maybe Eddie knows about those? No, I'm not. Yes. I know, just go search on nasa.gov for different internship programs and summer programs, and I will hand it off.
Yeah, I'm trying to think if JPL has any high school programs, and I know that there are 2 high school interns sitting down the hall from me this summer, so they must exist. So I think Googling, high school internships.
Undergraduates, the surf. Right?
Yes, there's surf for undergraduate students. I'm looking out. Josh is in the Earth and Space Science department. I don't know if you guys still have the Rockin' Out program. He's nodding his head. And I remember there were some astrobiology relevant activities, and we would go out as graduate students in ESS to high schools and middle schools in the Seattle area. And I remember I had a really cool astrobiology activity that we led with the students. So look into Rockin' Out. Oh, Surface Summer Undergraduate Research Fellowship. Yeah,
that's it. JPL and Caltech.
Anybody else have anything to add about pre-undergrad?
Next. We got a question over here. Oh, the next question.
Okay. Here's a really weird.
My question is, after you finish your PhD, how much room for maneuverability or transferring to a new field is there? Like, how much are you siloing yourself, both in a technical aspect, but also in a not technical aspect?
You want to start?
I would even add to that also, like, do you think that doing astrobiology has increased your maneuverability?
Yes, I can start. I would say astrobiology had greatly increased my maneuverability. So coming out of a technical PhD, astrobiology, to this earlier question that Megan asked, really demonstrated that I had the capacity to look at lots of different fields and synthesize them quickly and work across multiple disciplines, which is a broadly valuable skill no matter where you go. The other thing that Elena mentioned earlier is communication. And I think that this is something that you gain inherently in the astrobiology program and is also a valuable skill to really maximize if you're in grad school or even in undergrad, to be able to grant you more maneuverability, because the opportunity to be able to distill your science and communicate across diverse audiences is going to make you at least seem more maneuverable no matter what you do in grad school. And so I think that that is another really key skill to gain while you're studying. But broadly, I would say I think it made me more maneuverable because it was something that people always zero in on in resumes. They always want to hear about it, and so even if you're going into a different field, I think it makes you stand out from a lot of other applicants. In addition to the skills you gain.
Yeah, I'll just, because I left the academic track, so I just want to speak to this a little bit. You know, I was on the path of least resistance for a while. I went and I did my postdoc at Caltech for 2 years, and that was research based. I was writing proposals and papers, even though I was involved with the Mars 2020 science team. And so I had a lot of encouragement from my mentors to continue on that track. That would have been the obvious thing, to go apply for faculty positions. But I wasn't as excited about being strictly in the research world. I really wanted to work with missions and with people in this really collaborative way. And that was scary. And I remember feeling very anxious about leaving science to do this science adjacent career. But, you know, at least at JPL and at many other places, you end up finding your people. So I went and I found other people who had PhDs in planetary science, but were doing the systems engineering track. And I talked to them about how that transition went, and everybody was very encouraging. And so I think sometimes it can feel very scary to change what your path is. But I think the more you can talk to others, like, career panels like this are really great. We didn't really have anything like this when I was a grad student. So yeah, talking to people, and but it's very possible to kind of change tracks and be adjacent to what you were working on before.
Sure. Yeah, I would say that I did follow the traditional academic track, but the path I followed was only possible because of the interdisciplinary training I got. So I was in astronomy PhD graduate, but I went to an earth science department. It's earth and planetary science now, but it was an earth science department. There were no exoplanet astronomers, even in the astronomy department at the university I went to. And the reason I was able to do that is I was recruited by someone who had written a grant with this, interdisciplinary angle, but they didn't have someone that did what I did. And I was able to fit into that slot. And it was a huge risk, but partly I took that risk because I had a two-body problem in the sense that my spouse and I wanted to remain together and not be separated. And having that interdisciplinary training played a role in allowing me to continue on an academic track and remain in the same geographic area as remain with my spouse. So that can't be discounted. And I did explore other possibilities. I had a list of backup plans, and I found that, again, a lot of the things that were mentioned are true about being able to communicate in an interdisciplinary way, about being an analytical thinker, a quantitative thinker. And so I was in discussions with people I had met about going into the tech industry, and that was a possibility, if things hadn't worked out on the academic side.
So I'll finish off and say that I think maybe people don't realize just how broad the path forward is, even if you stay on the path. And Ty hasn't spoken up here, but we trained Ty in studying the Earth as an exoplanet. You know, this rocky world with oceans and all the rest of it. And you ended up doing brown dwarf science, right, in your postdoc. So one thing I'll let you in a little secret about a PhD. It's not really about the topic you're studying. It's about your personal growth as a scientist. So the whole point of a PhD, from the professor's point of view, is at the end of it to have someone who knows how to be a scientist at the end. And so it's not so much that you're training someone who's an expert in your particular subfield, but you have this broader goal of having someone who is able to think like a scientist. And people who think like a scientist are valuable in all sorts of fields. And so that's where, again, you can take in information, you can be analytical, you can write reports, you can synthesize results, you can hypothesize experiments, and so on. And so yeah, I think, you know, even those of us who've kept on the path have kind of bounced around from different topics. And I'll give another example. Jada Arni, who is one of my graduate students, her research was primarily on, it was kind of the overarch was hazy planets. But she spent a lot of time trying to understand the early Earth environments and what they would have been like. And she also did, you know, because I insist my students do look at least one planet in our solar system before they try and say things about exoplanets. She did one planet, one paper, one observation set on Venus, and she is now the deputy co-PI, co-deputy PI for the Da Vinci mission to Venus. So she now works at Goddard Space Flight Center. She works on Venus missions. But I mean, I would not say her PhD was Venus. So I think, you know, that it's just, again, it's if you have those basic skills, people can see that. If you're going into or applying for a job where they need the specific subject matter, the domain knowledge that you were trained in, sure, that's an advantage. But I don't think it really pins you down to doing that necessarily. And even if it does, even if you get your next postdoc in that area, you'll probably find you branch out while you're a postdoc, you'll start to do new areas of research. So, you know, as a scientist, you kind of fan out into all of these different interests. And so one of those other things you worked on in your postdoc might end up being your next step. And so, yeah, I don't think we all just funnel straight through exactly the topic we were trained in. I mean, look at me. I mean, I was trained on, you know, infrared instrumentation, which again is another broad type of thing. But, you know, I ended up leading a group of theoretical modelers doing, you know, studying how to find life on extrasolar planets. So.
Hi, that was actually a really great segue into my question. Is there something in your PhD that you think best prepared you for your current position? Something, or either something that you wish you had done during your graduate degree that you think would have best prepared you, or made your decision to either stay in the academic route or gone in the industry route?
I can start. I think one of the most important skills I got was giving presentations, and we keep coming back to this topic of communication, but like synthesizing and communicating the important bits of information in your domain. And so I'm, at least in ESS from the very beginning, and in astrobiology, we were giving presentations, technical presentations from the very beginning. And so learning how to do that was incredibly important. And I still use the same PowerPoint template that I developed in grad school for all my presentations still. But presenting is something that I found that I continued on. Yeah.
I'll say persuasive writing, which has applications far and wide. And so, especially as a professional scientist, it's often the case that I can't do the work that I want to do unless funding is provided, and so I have to write a proposal to win those funds, and so you have to write persuasively. And so, even more specific for my case is learning to write a proposal. And so I did have opportunities as a graduate student first to start off and like kind of writing sections of proposals, and by the time I was graduating, writing fellowship applications, which are multiple pages of coming up with new ideas and persuading someone that you could actually do that science and you're the right person to do that science. And so persuasive writing has been an absolutely essential skill.
Yeah, and this is down to a PhD as sort of general training to become a scientist, and the suite of skills that you learn. And I think for me, the thing that was missing in my PhD, you guys are all going to laugh. But the thing that was missing in my PhD was this persuasive writing component. I didn't really get to write a proposal in my PhD. And I understood as soon as I hit JPL, and we were all soft money scientists, right? So soft money means we didn't have any dedicated funding. We had to fight for our funding tooth and nail, get it either from, internal funding sources or from government sources as well. I realized that was a hole in my background. And so that's why I now run a professional development course at the University of Washington in astrobiology. And we have one strand that is just proposal writing and sort of how to do that. Because I think, one thing my advisor at JPL said, which has always been true, is he said, the great thing about science is you can do absolutely anything you want that you can convince someone else to fund. Okay. And that is the freedom of science, but it's also its constraint that you have to be able to get funding from people. So so that's one thing. So honestly, the other thing too is that being a communicator and a good communicator ends up being the thing that will leverage you up into PI-ship or leadership, because again, you do have to write reports and be in persuasive writing. So if math is not necessarily your strong suit, but you're a really great writer, that actually is really useful in science, and that is something that we need to try and train in PhDs as well.
Yeah, I just want to really quickly add, being able to get out of your comfort zone, particularly for networking purposes, being able to put yourself out there, cold email someone if you have a question, a scientific question, or if you want to build a collaboration. The answer can be no, but putting yourself out there can gain you those opportunities. Traveling, going to conferences. Sometimes these things can be intimidating. A lot of people will jump at the opportunity. Some people will be intimidated about it. And it's really important to be able to just push a little bit on your comfort level, to take some risks, and put yourself out there.
Okay. Hi, everyone. Awesome panel so far. My question is about kind of how you decide or discover what you're interested in at like higher and higher levels. Like the anecdotes about, looking at the moon or paleontology for three of you. But at like higher levels, or like, and that guides, like your early career, but then later, honing in on something that even sounds as specific as like modeling planetary atmospheres is still a gigantic number of things. That could be the weather, or transit spectroscopy and retrievals. And so I was wondering kind of what guides you all on, these, when you have to make these very like fine scale distinctions and choices about what you're interested at your like high level careers and what to work on next, as somebody who hopefully can do this one day.
Holding the mic so I can start. I think one skill that's really important is understanding where the field is and what open questions are, one, compelling, and two, answerable with the tools that you have or you can gain in a period of time. Of course, we're studying this stuff because we're interested in it. But as Vicky said, writing proposals is really important. You can't do the science unless you have the money. And so identifying those open questions that you can contribute to.
Yeah, I'll add kind of similar to that. I was thinking in my head, like, where's the wind blowing with respect to like funding these days? In my field, there probably won't be any more Mars rovers after Perseverance. That's probably the last big flagship Mars rover. So I can't do this forever. So I've been going to a bunch of lunar seminars at JPL because that's probably the next frontier for NASA robotic missions in collaboration with human spaceflight. So JPL will probably consider how to enter that world. And so I've been learning about the moon and what kind of science we want to do on the moon, and then using my particular skill set. Okay, so how do you do that science? What kind of instruments do we need to build? What kind of measurements do we need to take? I don't know if anyone knows what a science traceability matrix is, but yay. What is the science question you're trying to ask? How do you answer it? What kind of measurement do you need to take? And then how do you do that? So thinking about that, about the moon. And so there is this bit, at the end of the day, this is a job. And so I want to continue having a job. And so where's the wind blowing in terms of funding, at least for me?
Um, yeah, I think actually, no, you go, Ty, and I'll finish up.
So there were kind of two parts to that question that for me are very related. And so there's the how did I find what it is that I'm interested and enjoy doing? And then how do I end up doing the things that I end up doing? And I actually think about my career as being, I have this space over here of things that I really enjoy doing. And the way I assess that is like when I have a day to myself or I don't have any other commitments, what is it that I want to be spending my time on? And it's often like, sometimes it's super nerdy science things that really have no application. And then here's the other side of here of space that is things that the field needs, things that would benefit the field, things that might secure funding. And so then you have, for me, I've tried to make sure that I have overlapped those two somewhere in a Venn diagram, and where those two overlap is kind of where you can have a career where you've got funding and you can do the kinds of things that you enjoy. There's no issue with having other things that you enjoy working on and spending time on that. Sometimes that can develop into stuff that eventually gets funded and is useful. But so I'm adding more weight to like paying attention to where the field is going, what the field needs, and how your skill set could add to that.
Notes down here, and then I'll hand it off to Vicky to finish. I think Elena alluded to this a little bit with like looking at how the wind is blowing, but I think like letting yourself be open to lots of different possibilities is really key. I think, I don't know if it's fair to say for the rest of you, but I think a lot of people end up where they are just partially through chance, and there's like a lot of beauty and opportunity in that. Even if it's not necessarily where you thought you were going to go, you might discover something that just like really like lights your fire. One piece of advice I heard when I was like totally changing careers is not to let who you used to think you are like define who you are in the future, right? So for me, that was like, I'm an oceanographer, I'm an astrobiologist, but I'm interested in lots of different things. So not to be too stuck into that field. And then like a piece of really tangible advice that I give to people that I supervise now who are asking the same question is when you're like going through your daily life, take note of the tasks that you really enjoy and the tasks that you really don't, because I think that's really key too. You might enjoy certain questions and that'll change over time, but there are going to be certain aspects of a job or a role that you'll really enjoy. And if you pursue those, I think you might find more satisfaction over time.
Yeah, okay, so that was a great segue because that's actually my point, is that often you don't get to choose where you end up. But part of it is absolutely staying open to things. So I would say for me, I mean, you can look at my my trajectory as like a whole series of interesting accidents that happened, and more things kind of happened to me than I had control over. But it's okay, it worked out in the end. And even the VPL, I mean, I was told to write the proposal for the VPL. That was not my original intent, and yet it has defined my entire career. And so at JPL, basically, they said, oh, there's this great new opportunity opening up. We need somebody who's not too busy to write this thing. You. I didn't step backwards fast enough. You write this thing. And I looked at it and said, oh, it's kind of combining earth science and planetary science and astronomy, and I'm interested in all of those things. And so, maybe this will be okay. But I mean, never discount fate because things will come up, and you have to look at them and say, is this something I can do? Or, in my case, you'll be told to write this proposal. And so I think, yeah, I don't want to give the impression that you kind of just choose every single step of the way. It really is this sort of synergy between, I think it's more true as you get later on, but early on, you'll be guided by what your advisor has money for. And again, that is one of the key responsibilities of an advisor, is to tell you which way the wind is blowing, to choose a good topic, or at least tell you the area in which you should choose a good topic. And so, yeah, a lot of it is really an interplay between what the universe does to you and then what you would like to actually learn and do.
Can I add one small thing, which is, sometimes you'll try something new too and realize like you don't like it, and it's okay to say, I don't want to do this anymore. So at JPL, last year I took on a very small 20%, 10% time project and tried it for a year and then realized this is not a good fit for me, and was able to pivot away from that. So I think also giving yourself grace to say like, oh, that was not a good fit. I don't want to do this anymore. I contributed my bit and now I'm going to step away.
Okay, since I have the mic, I would like to ask a question. What is something that you wish or would love to tell your younger self? Like some nugget of wisdom or just something that you wish you knew early on in your career path?
I need to think about that. Does anyone have something prepared?
Yeah. Start writing now. And Yeah, I think oftentimes a mistake people make, especially in the beginning, is I'm going to do all the science and I'm going to write it up, and that is a bad way to do science. What you should do is write everything you know. I mean, you should be writing the introduction to your paper, draft one of like 30, as you're doing your background reading, um, and keep up on that and have a system. And I think, that's the advice I would give to my younger self. And the younger, the more useful it would have been.
Oh yeah, and another practical good one is back up your data in multiple places. I have kind of just like enjoy it while you're in it. Enjoy whatever step you are in the process because you don't get it back. When you're an undergrad, try to enjoy it as much as it's, tough staying up late working on problem sets. When you're a grad student and you're feeling stressed out that there's no way you can graduate, take a deep breath and realize you will graduate. It's going to be okay. And try to enjoy every step that you're in because, yeah, it's a beautiful thing. I wish I could be in school forever. Like, this is a wonderful place, academia in general. So try to enjoy the moment.
I think one thing that it took me a while in grad school to realize is that no one else was as invested in my degree as I was, or at least should be. And that was really enlightening to me because it allowed me to realize that I could basically pursue the things that I wanted to and sort of like craft that into my career. And I think that's something that relates a lot to the last question, where there are a lot of things that happen to you throughout your life. There's also a lot of things that you have the capacity to influence, and it's something that you want to be proactive about and pursuing the directions that you're most interested in, rather than pursuing like this, necessarily the path of least resistance if that's not something that you're focused on or interested in.
I think I would just add, it's kind of a trait thing that I would tell my younger self, that it's all going to be okay. And so Vicky kind of talked about how lots of things kind of happen to you as you're on your academic path. And so there's a lot of uncertainty on any career path, and certainly on my career path, there are multiple instances where I didn't know if the next thing was going to come through, and so I was having to think about other plans for what would happen if that thing didn't come through. And so knowing that it's all going to be fine in the end would be important to know way back when. For students that I work with now, especially my PhD students, I like to point out that the unemployment rate for people with PhDs is exceptionally low. And so you're going to find something to do with your PhD. And as we've discussed already, it's because you've been trained in problem solving and you have these broad skill sets that make you very employable. And so I think my younger self also probably should have known that, like, you're going to have a job, it's going to be fine. And so I would have liked to have heard that.
Okay. And maybe this is sort of a more personal thing because of my role as a minority in science, is that I would have told my younger self that, you know what, you're actually better at this than you think you are. And I think I was probably one of my own harshest critics. And I would advise my former self to maybe go and talk to the people around me and see how they perceived me, instead of sort of living in this bubble of thinking that I had to always do better and work harder. And I mean, that's partly true, but I think, yeah, sometimes our own self-perception of how we're doing is not really that accurate. That it would be good to go and talk to other people who, are willing to give you, find someone you trust enough to give you actual, true, feedback on where your strengths and weaknesses are. Because I think that would have been super useful to me early on.
Hi. Another question I had was, are there guidelines being developed for the proliferation of life beyond our biosphere, like perhaps on the moon or in other places? And what are the ethical considerations around that, as at least how it relates to astrobiology? Thank you. Yeah, like the proliferation of life beyond Earth. So spreading life from Earth to the moon or somewhere else.
I'm planter, yeah.
Yeah.
You want to talk to them?
Okay. Actually, I think you should answer it. This is a really important question, and that's actually one that we tackle in my ethics and astrobiology seminar. So we run a seminar partly based on what we have at the University of Washington, which is in ethics and astrobiology. to look at things like planetary protection, right? So planetary protection is the idea that, one, we don't want to bring bad things back here, but more probably the bigger danger is that we would bring some Earth life somewhere else, and it could be bad for a couple of reasons. One, if we're looking for life, we don't want to find life that we brought. And also, people give intrinsic value. Depending on your value system, you might give value to life that already exists there. Some people give value to just sterile landscapes, right? Actually, and there's a few books that you can look into. There's Encountering Life in the Universe. There's a few others, and these are collections of essays by people who are not necessarily scientists, but philosophers, theologians, some scientists thinking about what are the ethical implications of this, and even is there an ethical impetus to spread life, to terraform Mars or something like that. And if you're looking for a clean answer to that question, we're not going to be able to provide that for you. But there are a lot of very smart people who've thought of the implications of that question.
Yeah, I don't have much to add other than I'm really glad you're teaching an ethics course in astrobiology, because that was one of my favorite classes we took here. But we take planetary protection very seriously at JPL, and from the standpoint of sending microbes to other planets, mostly in our case because we're looking for evidence of life, so you don't want to accidentally bring your life and detect your own life, right? But also we don't want to land in the polar caps and potentially melt some ice and create a little habitat, and then who knows what that means. So people are thinking about it. It's not necessarily my job though.
Hi, yeah. I as a undergrad, I'm kind of curious what your like actual day-to-day work is like what you spend your time doing, split between different things, and yeah.
Do you want to start and we'll go down?
Right, the most depressing one first. Okay, so so I'm the director of this program. I also run a large research group. I also have teaching responsibilities. I have service responsibilities. I mean, day to day, it's a lot of Zoom meetings. So day to day, it's a lot of Zoom. I'm spoiled right now because I'm on sabbatical, so I get more time to do research. So I actually have entire days where I just get to sit down and like work on papers. But I'm still actually working on other people's papers at the moment and not getting a chance to think about my own. But I'm going to change that around in summer. But yeah, so typically it's meetings with collaborators. It's meetings with any service things I'm doing for NASA, for example. I in the past, at least, I spent a lot of time working for NASA on various committees and things. So we would do that. It's teaching. It's it's discussions about running the program. I mean, it's a lot of both administrative and organizational, and then you squeeze the science in whenever you can. But I am at that stage of life where that is kind of typical. Younger scientists actually, okay, I'll tell you, this is a really funny diagram that someone, I think at Cambridge, showed me, but it's a square and it has a cross in it, and it's got an axis that says, basically time since you started getting interested in being a scientist, and then this is sort of the total fraction of your day. And over at the edge here, there's research. So when you're a young scientist, all your time is research. But as you progress across the diagram, these other squares are teaching and administration, and then the final one is lunches and dinners. Okay, so as you progress, being a scientist, you go from all of your time being research to a smaller and smaller fraction of it being research till you're overwhelmed by science administration. And then finally, they just drag you out whenever there's a visiting dignitary and make you go to lunch or dinner. So, I'm kind of that progression where I'm starting to hit up on the lunches and dinners. It is happening. So my life is mostly teaching and administration, except when I get a chance, like on a sabbatical or in the summers, to sort of, bring my research in. But that being said, part of my job is advising my students. So a lot of my week is meeting with students, having group meetings. So the science comes in because the students force me to do the science, and that's great. That's a happy thing. But yeah, doing my own individual science, I don't get as much time for that anymore.
Okay, so I wear two hats on the Curiosity rover. One is like an operations role. So I'm the science operations coordinator. So I do tactical shifts about 3 days a week, and it is so much fun. So I wake up at 7:45 and I get to see the first images downlinked from Mars from the day before's drive, and I'm like one of 10 people who get to see the pretty rock that no one else has ever seen before. It's really fun. So a lot of my time is doing ops, working with the scientists, this quick paced, trying to figure out what observations we're going to sequence and send up to the rover. And then the other part of my time wearing my team chief hat is figuring out, like, strategically, how do we do that? I have to manage a budget. I have to, allocate money to. I'm doing this for fiscal year 25 right now. I have to work with scientists and make sure they have all the tools that they need. A big thing that I'm dealing with right now is cybersecurity from NASA. Making sure that folks aren't getting into our JPL's network and potentially doing nefarious things. There's a lot of time spent thinking about cybersecurity, sending emails, communicating with people, presenting technical information both to the scientists or scientific information to the engineers. And yeah, a lot of strategic planning. So thinking about what do we want to be doing, especially with the Curiosity rover. What are we going to be doing in 2 years, in 5 years? Like, how much energy do we have left as our plutonium, releases less heat? How are we going to continue operating our rover with less and less energy and still get the science observations that we want? So a lot of strategic planning is the other part of my day.
Yeah, it really varies depending on if there's a grant deadline coming up. Or if it's a conference, that pie chart of like the time spent doing various activities looks very different depending on when you are in the academic year for professors, and what grants are due at a certain time, what reports are due at a certain time, and so there are weeks where it's all writing, and meetings because you always have meetings, and emails because you always have emails, but you really try to dial those back. And a lot of time spent in front of a computer, coding or running models, or again, answering emails, often presenting technical information. And then depending on the quarter, for me, teaching can be a huge time sink, or it can be a smaller one. So I once a year teach a 300-person class, and not just from giving the lectures, but also there's a lot of time answering student emails and answering questions and meeting with students. And even if only a small fraction of them need extra help, that can take a huge portion of your time.
So my response is somewhat similar to Eddie's, because I'm also faculty at a university. And so I was trying to think of this as like averaged over the academic year and summer, what does an 8-hour day kind of look like for me? And so a couple of those hours would be spent developing course materials and teaching. An hour of that time would probably be spent doing administrative work. And so this is like drafting budgets and submitting reports and things that I have to do. There would be 1 or 2 hours of work that is generally called service, meaning that I'm helping out for some seminar for our department, or I'm helping some committee for our department. Similarly, at the national level, there are things that I'm involved in that I have to help out with. There's probably 1 or 2 hours spent working with students and collaborating with students on their research and helping them grow as researchers. A couple of hours spent coding and writing up my next publication, and then maybe an hour or so thinking about science generally, and what the next thing needs to be. Those didn't total to 8, which is another important thing about being a scientist, is that it follows you home at night. And so sometimes that means that, like, I've mismanaged my deadlines and things have caught up to me, and I have to go home, and after my kid goes to bed, I need to write a document for a couple of hours. It's not always like that. Sometimes it's like that. But the thing that always follows you home as a scientist, and this is true of other careers too, is that, like, you're always thinking, even when you go home at night, about how am I going to improve that paragraph in the proposal that I'm writing, or what's the next deadline that I've got, and starting to draft the thing that you're going to write for that, or what's the next paper I need to be working on. So it always has your brain going, even at night.
That's not really the case for me. One thing I really like about being at the state is there's really good work-life balance. Most people will clock out at 5, and that's pretty much the end of the day. So in my role, I work for a statewide elected official, Commissioner of Public Lands, Hillary Franz. And so there are moments where we do a lot of, fire drills and have to respond in the evenings. But overall, the vast majority of my job is facilitating and making sure that the right people are in the right place to talk to each other. So a lot of meetings, a lot of strategy development, tracking implementation. We have sort of a seasonal cycle. January starts Washington State legislative session. So we're writing bills, working with legislators to get things to push through. Spring and summer, we have a little bit more flexibility to do actual implementation. We get to go out in the field and touch some trees and go on boat tours and talk to oyster farmers. We do a lot of stakeholder engagement, a lot of tribal consultation and public meetings, but generally pretty variable day to day.
Just because this triggered something in me. What Ty was saying, and this comes back to the question of what skill you wish you had learned in grad school, and that's time management. It's so important, and I was a terrible time manager in grad school and got better as a postdoc, and now have to be really good at it. And I think that's just something that will benefit you in any career you go down, but time management. Sorry, I just had to bring it up.
The question is, how do you avoid getting burnt out? It's for the Zoom.
You want to start?
No, I'll finish.
I mean, I will say very similar to Max. I have a very good work-life balance and mostly work 9 to 5, except for in anomaly situations or when there's an important deadline or, but those are not the rule. It's the exception. But this is one of the reasons I did not continue on the academic track, is that I really wanted to have that proper balance and I didn't have it as a postdoc, and I was getting burnt out, and I needed to make that kind of career shift in order to not do that. So finding things that fill your cup are really important. Sorry, now I lost who asked the question. Oh, there you are. Okay. Find the thing that fills your cup and make it a priority is really important.
Yeah, I'd say having things outside of work life that you value is really important. And learn how to say no. I'm horrible at that. And I'm trying to learn to get better. I once read a book, and I don't remember anything else except for the fact that it had a bit of advice, which is that we often look to increase our tolerance to stress in order to be less stressed. But that's actually not a good way to be less stressed. You actually want to decrease your tolerance to stress because you're just going to equilibrate to the maximum amount of stress that you can tolerate. And in academia, at least, you often will just absorb as many tasks as you have capacity for. And it's really easy to end up with a non-optimal distribution of those tasks.
I was just going to acknowledge that burnout is very much a thing, and I certainly experience it, but I don't view it as like an on-off state. And so I picture myself as having this gauge that sometimes approaches burnout. And so for me, it's been making sure that I'm self-reflecting on how I'm feeling about burnout, and then assessing what it is that I'm currently engaged in that is driving the burnout feelings. Because there are aspects of what I do that I absolutely love, and they never contribute to my burnout. And then there are aspects of what I do that when I have too much of that on my plate is what contributes to the burnout. And so it's about managing the balance of those two things. And then having things outside of work, family and hobbies and things like that I know I'm going to be able to go home to on the weekend and not think about the things that contribute to the burnout.
One thing that was really hard for me when I transitioned out of science and into science policy was that I felt like I was losing a big chunk of my identity. And I realized that when I was in grad school, the whole way I defined myself was as a polar oceanographer. And I didn't really have a sense of who I was outside of that. And I think that's something that really contributes to burnout, because you don't have this space beyond the work that you do. And similar to what the others are saying, there's always going to be more work to do. And most of the time, there's no such thing as an astrobiology emergency. There's probably limited cases with rovers and things, right? But rarely, this is something I think about now too, like there's no kelp and eelgrass emergency other than like, the, chronic challenge of climate change. But so that's something that has really helped me redefine that there's always more work. So being able to bracket it within this role in your life and recognize that there's other important pieces too helps me prevent burnout.
Yeah, I'll just finish up and say that, Eddie's right. You will absorb everything that is thrown your way unless you try and set boundaries. And I'm very bad at it too. So you just have to learn to say no, and try and see the bigger picture and the other thing too, again, as a minority, they will come at you. They always want women on their panels, and I suddenly realized, oh, I'm being asked to do all of these things not because I'm truly necessary here, but because they're trying to fill their quotas, and once I realized that, I'm like, okay, there's other people who could potentially do this, but the thing is, if you promote a junior colleague, sometimes they won't take them for whatever reasons. So yeah, I think it's, for me, I did get burnt out last year, so I've experienced that. And yeah, I just turned around and I said, no, I just can't do this anymore. No, 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 no. And I think too, also for younger people, I think there's also this sense of, oh, NASA came and asked me to do this thing. I must do this thing for NASA. And I've literally had students come to me and say, oh, well, I turned down this panel. Is this terrible? Will they never ask me again? I said, oh no, they'll be back. So also realizing that if you say no to something, it doesn't mean you've cut off an avenue in your career. So I mean, I think that's part of the balance, is just realizing in the end, you want to do what you want to do, not because you feel an obligation to the community, which is kind of one of my value systems. And so I do tend to overcommit to doing things with the community. But also, what is of interest to you? I try to tell my younger people to strategically pick things that are really going to advance your career, because some of the things will. And I mean, one of the reasons my career really took off was because I did overcommit to doing service for NASA early on, but that meant everybody at NASA headquarters knew me. And that actually helped. So that's another thing that they kind of don't teach you. It's the hidden curriculum, is it's not just writing a good proposal. It's that networking. It's who you know, and it's who you've done things for. And so there was kind of a barter system early on where you would do things for NASA headquarters and you got the profile, and they knew you were a good person for that. But then they'll take advantage of that. So you just need to try and dial it back. So yeah, learn to say no. And prioritize those things that you enjoy doing and that will also advance your career, rather than things where they just need a body for whatever they're doing.
Maybe just to add to that, especially if you're a grad student, is find good mentors to help you navigate which are the strategic things to do, because as a graduate student, you don't know. So really finding someone who can mentor you, and you can talk to them about all the opportunities or different paths, and they can help you go through the list of what really will help you.
All right. Well, I think that's all the time that we have for our panel, but thank you all so much for being here and on Zoom. And if we could thank our panelists one more time for their time. Great. And then, as Vicky mentioned, I just want to point out that this is one of the 25th anniversary celebratory events for the astrobiology program. The next one should be in August, and we'll be doing an open house, which will have a lot more opportunity to interact with different people in the program and to learn about the science that's going on. In the fall, we will be having a lecture series also from alumni of the program. All right. Thank you.